Is there's nothing is excluded, is it? I mean, eventually everybody gets accounted for. Every piece of 0, 1 participates in a subinterval that has a rectangle on top. So how do we add this baby up? Well, it's 1/2 times the sum from k equals 1 to infinity. Let's see, I have a third, 2/9, 4/27. How's this going? It's like, it's 2 to the k minus 1 over 3 to the k. Multiply and divide by 2. Okay? So that's going to be 1/4 sum k equals 1 to infinity, 2/3 to the k. That's geometric. So it's 1/4. First term is 2/3. I think that's a half overall, isn't it?
Yes.
2/3 over 1/3 is 2. 2 over 4 is 1. So the integral, the Cauchy integral. Of course, what I'm doing is my partition. I always use the left end of these little rectangles. You know, I successively refine the partitions, and it approaches this left. You know, my first partition would be here, 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 and here. The next one I go here, 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 here. You know, keep going, and always a finite set, pretty big finite set. And as the normal partition gets smaller and smaller, I can show that I'll approach 1/2. Let me find what the problem is. That problem is exercise 3.11.1. Would somebody like to do the second part of that exercise? 69. The Cauchy integral from 0 to 1 of x times the Cantor function. What's that? There, I got you started. We integrated the Cantor function. What if you multiply that by x? Would you be getting little triangles? Maybe. Would you? And maybe you could be clever about adding the extra area where. Somebody want to try that? Wendy, have you accepted the challenge? She's going to explain the Volterra example. Somebody want to do this integral next week? I know Rob's dying. Okay. You want to try? Okay. You get stuck, Paul. All right. So there you go. That's the integral of the Cantor function. And then the Volterra example you're going to do is based on the Cantor idea. Remember on the practice exam, I didn't put this on the real exam. I talked about SVC sets, Smith, Volterra, Cantor sets. Volterra starts out on page 70 there, designing a set, a Cantor set of positive measure, a Cantor-like set of positive measure. And he wants the positive measure to be 1/2. So how do you get that? You want what you take away to add up to 1/2 to leave the 1/2 upon which you're going to define something. Right? So I need a geometric series that sums to 1/2. What if we took away, how about the third one? If we take away thirds, that adds up to 1, right? What if we take away quarters? How's that work? Okay. Middle quarters. Does that even work? divide this into 4 pieces, we can take that away. Divide this into 4 pieces, we can take that away. So what's left here? That's a quarter, 16, 16, 16, 16 cents. 4/15. I think 4/16 was a quarter. So I'm taking away too much. I'm taking away too much.
Yeah, you have to, because you started off taking walk and half, you want to find something to eat.
Try this again. Let's go an 1/8 on either side. So that's a quarter going. So this point is 3/8, and this point is 5/8. And we have 2/8, 1/8, 6/8, 7/8, and 8/8. So we're going to take, now what? We go to the middle of this, and then take, if we go to the middle, if this is an 1/8 and this is a quarter, then this is 3/16. So if I go to a 16th on either side, it's starting to look like this, right? So I take away a quarter, a total of a quarter, and then I take away 2/16. What's this add up to? First term is a quarter. Constant ratio is a half. Quarter over a half is 1/2. So that's the Vito-Volterra Cantor set. Well, Smith-Volterra Cantor set with residual measure 1/2 that I was talking. So when Burke says, let's ignore a Cantor set of positive measure, say 1/2. That's it. That's the one. So that Volterra constructs a function which has a disastrously discontinuous derivative. But it's defined, but it's just horribly discontinuous. Bounded, defined, not continuous, not everything. So Wendy's going to explain that to us. All right. All right. I want to go back a little bit. The reason I'm going fast to the Riemann stuff is, and into the Riemann-Stieltjes stuff, is because a Riemann-Stieltjes integral looks like this. From A to B, F, D, what's the year's phi? Phi? Every one of these is a Riemann integral if phi equals x, then it's a Riemann integral. So if you work out the theory for Riemann-Stieltjes, the Riemann part comes along naturally. Okay? The Riemann integral is extremely like the Cauchy integral, which we went into in great detail. You just move the tag points to be more general. You go through all the same kinds of proofs, and you get that. I'm going to put on the net the major results, and I'm going to put my own proofs out there in sort of a chattier style and book here. He skips a lot of them. I would like to put out there the super result, as far as Riemann integration is concerned, is the 19-2 theorem with Bouvet that gives necessary and sufficient conditions for Riemann integrability. Bounded and continuous almost everywhere. Necessary and sufficient.
But I got now, conclude that it's continuous concern.
Well, yes, but it has to be bounded. It can't be, you can't say if it's Riemann integral, it's continuous almost everywhere because it has to be bounded. You can't be like 1 over x on 0. Okay. I'd like to call your attention to the business on the Cantor function. On page 69 again, Burke, in order to show that the Cantor function is continuous and hence integrable in the Cauchy or Riemann-Stieltjes sense, that the convergence is uniform.